Let's see, should we go ahead and get started? So today we're very happy to have a second lecture by Yifan, and just as a reminder to everyone, please feel free to ask questions either over chat or just unmute yourself and ask a question. If you have a question about something, probably many other people do as well. So thank you, Yifan.
Thank you, Ken, and thanks to everyone who's tuning in for the second lecture. So last time I talked about the field theory approach, a Lagrangian approach to study 42 superconformal field theories, and some kind of bottom-up classification program. I briefly reviewed this bottom-up classification program for lower rank SCFTs based on studying scale invariant Coulomb branch geometries. Today, I'll talk about a top-down approach that constructs 40 into 2 superconformal field theories from geometry. Okay, and I'll give two specific constructions. One comes from class S. Well, one is the so-called class S construction that comes from 2,0 theory, reduced on the Riemann surface potentially with punctures, and another construction coming from type 2b on threefold Clavier singularities. There are also other constructions, which I'll mention towards the end. And just to, as a prelude to what Fabio will talk about later today, I'll also give a brief introduction to 5D into 1 SCFD based on from the perspective of the effective theory again, okay, similarly to the last lecture. Okay. So the main hero today will be, for the class S construction, will be the 2,0 theory. So let me say a few things about that. The 2,0 theory is the maximal superconformal field theory in several ways. First of all, it's the superconformal field theory that can exist in the maximal possible dimension, which is 6th dimension. It also has the maximal supersymmetry. The superconformal algebra of the theory is this OSP 8*/4. It contains the bosonic subgroup SO 6,2, as well as R symmetry SO 5. Okay. This theory, as I mentioned in the beginning of last lecture, has a ADE classification, and this is there's some old argument, and more recently there's some nice argument due to Cordova, Dumitrescu, and Ying in 2015 that uses the compactification of the 2,0 theory on the circle. There's a top-down construction of these theories. Top-down construction of these theories exist both in M theory and in type 2b. Initially, the vanilla type 2,0 theory of the A type was constructed by looking at a stack of N and phi branes in M theory and taking a decoupling limit and zoom onto the low energy dynamics on the M phi brane, where the effective theory is described by this 2,0 theory. And later, it was realized that the more general 2,0 theory of the ADE type can be realized by type 2b probing a twofold singularity, ADE singularity, where after you decouple gravity, the residual degrees freedom are live on this 6-dimensional transverse space. The 2,0 theories are isolated among all possible supersymmetric theory in 6 dimensions. 2,0 supersymmetric theory in 6 dimensions, because the conformal theory itself doesn't admit any marginal or relevant deformations. Okay, this is due to some general classification results of Clay, Thomas, and Ken. Okay. But the 2,0 theory does have a moduli space, which you can use to deform the theory to some free description. And the moduli space in this case takes the form of R5R. So it's if your ADE Lie algebra is of the rank R type, then the moduli space is R5 to the R, modeled out by the Wall group associated with your simply laced Lie algebra. In particular, SO5, the R symmetry acts on this moduli space in a very simple way, where this R5 just transforms as a vector representation. More abstractly, you can think about this moduli space as generated by vevs of half BPS operators in this particular R symmetry representation, thinking label k, 0. this operator has dimension equal to 2 times the thinking label k, thanks to the shortening condition. Okay. Schematically, in analogy to what you may have seen in 4 dimensions, is that these operators can be schematically represented as trace phi to the k, where phi is something transforming the adjoint representation of the ADE Lie algebra. But this I emphasize is the schematic because this 2,0 theory is not a gauge theory in any ordinary sense. I also want to emphasize that this half BPS spectrum of half BPS operators are coincide with the set of fundamental degrees associated with the simple Lie algebra. So, for example, for the A type, it will just be for AN type 2,0 theory will be all the way from 2 to n plus 1 and so on. Okay. Right. I just want to make one comment here in relation to a question that was asked yesterday about whether there's a rank 0 2,0 theory. So as you can see, so if you study the representation theory of the 60 STFT, you see that the stress tensor multiplet sits in the particular half BPS multiplet of the type with the bottom component that's a half BPS operator with k equal to 2. So automatically, if you have a CFT with 2,0 supersymmetry, there has to be a half BPS operator which you can use to parameterize the moduli space. So in that sense, there's no rank 0 2,0 CFT. Okay, so that's a quick argument. The 2,0 theory on the tensor branch has a rather rich structure that's coming from some BPS objects known as the self-dual BPS strings, whose tensions are related to the tensor branch event. Okay, and this the tensor branch effective theory, as Cantoro and Fabio both talked about, involve this tensor fields, self-dual tensors d mu nu, and these self-dual strings are charged under these self-dual tensors. That's why they're called self-dual. Typically, the 2,0 theory itself is, as I said, it doesn't have marginal relevant coupling. There's no Lagrangian, so it's very hard to describe it. But one useful description of the 2,0 theory that we use very often is this reduction on S1. In which case, just by supersymmetry, it has to be described by some five-dimensional maximal super-Yamil's theory, which is free in IR, and by and with the same whose gauge group is given by the correspond is the one associated with the ADE Lie algebra that labels the 2,0 theory. And you may think that doing this reduction procedure, you will lose many features of the 2,0 theory, like for example the KK modes on S1. But this is fortunately not the case because there's a correspondence between the KK modes on the S1 reduction and Yamil's instanton in the 5D super Yamil's theory. So just to remind you, these are like the ordinary instantons you encounter in 4D gauge theories. They are codimension 4, but in 5 dimension it becomes particles. And the claim is that these particles precisely correspond to the KK modes on S1. So in some sense, you still keep the information of the 6D theory when you use this 5D super Yamil's description. Okay, and there has been lots of work. A lot of work in literature has been trying to extract information about the 2,0 theory from the 5D super Yamil's, taking into account all these instanton contributions. Well, you can go one step further and compactify the theory on another circle, or altogether compactify the theory on the Riemann surface. And naturally, you expect to in the low-energy limit to construct some 4D quantum field theories, and this is the logic we'll pursue in this talk. Okay, so before we compactify a general interacting 2,0 theory, let's look at a simpler case. Okay, so recall that this EFT of a general 4D include 2 superconformal field theory is described in the last lecture by the so-called subweighting geometry. Okay, so in the subweighting geometry, what you have is you have some Coulomb branch, and you have some 4D2 vector multiplets that parameterize the Coulomb branch and its excitations. And this effective action can be described by a pair that is the subweighting curve and the subweighting differential. This pair determines the prepotential, which in turn determines the dynamics of the vector multiplets on the Coulomb branch. So last time we asked the question whether there's some physical meaning to this very nice geometric structure, and the answer is yes. So you can capture all this information about this 4D effective theory on this Coulomb branch by a 60 free, in other words, U1 2,0 theory reduced on this Seiberg-Witten curve. Okay. And that gives the 4D effective theory. So how does it work? For example, in the 4D effective theory, you have the gauge field, the photon, and you also have the dual photon. Okay, that's coming from electromagnetic duality, and this pair directly in this reduction perspective directly comes from reducing the self-2 form, which describes the abelian 2,0 theory reduced down cycles on this Seiberg-Witten curve. Okay. When you reduce it on the when you look at the canonical basis of these cycles, and naturally when you reduce on the cycle and this dual, you give rise to the dual pair of photons in 4 dimensions. And also we mentioned that the mass of the BPS particles are given by integral of the Seiberg-Witten differential lambda over 1 cycles. Okay. And from this 60 perspective, these BPS particles are naturally coming from BPS strings wrapping the 1 cycles. Okay. And from the M theory perspective, these are coming from certain supersymmetric M2 branes. Okay. And the infinitesimal tension of these M2 branes are precisely given by the this infinitesimal tension of the M2 branes, which extends in one other transverse direction, naturally give rise to the Seiberg-Witten differential lambda. Okay. So here, I just want to emphasize that here is we have lifted the 4D Coulomb branch physics effectively to a 60 free theory. Okay. But whether this 60 free theory has a UV completion as some interacting theory is still a question, and that's what we'll come to next. Okay, and here is what here is where the class S construction comes in. So starting from this 60 free theory on the Riemann surface, which we described just now, there's a lift to some interacting theory reduced on a different Riemann surface, C. Okay? The relation between C and this Seiberg-Witten curve will become clear shortly. This curve C is a Riemann surface, and is usually called the UV curve, or sometimes called the Gaotto curve, thanks to the work of Gaotto. Okay, and the idea is that if you consider 2,0 theory wrapping this curve, or in other words, a stack of M5 branes wrapping this curve, in the low energy limit, the effective dynamics of the transverse excitation of the M5 branes are essentially described by a single M5 brane wrapping the IR curve, also known as the Seiberg-Witten curve. Okay, so let's be more specific about the setup. So, we want the setup to preserve 14-2 supersymmetry, right? So to preserve the supersymmetry, as you probably all know, we need to consider special kind of geometries. So the ambient space is M theory on this geometry. It involves some flat directions that will be identified with the space-time direction of the 4D theory. It involves some non-flat directions, which is the cotangent bundle of this Riemann surface that essentially satisfy the Calabi-Yau condition. And there's also another 3 transverse directions whose meaning to the 4D theory will be related to the Higgs branch, which we'll comment on later. In this ambient space, there's a supersymmetric M5 branes that wrap, which extend into this 4 space-time directions, and also wrap the 0 section of this cotangent bundle. In other words, just the Riemann surface C. Okay, and this is the stack of M5 branes effectively described by some 2,0 theory. And when you compactify the theory on C, as we'll see, this will give rise to the 14-2 theory. You can make this picture richer by including what's known as defect M5 branes. Okay, these are M5 branes which are again supersymmetric they share the same four longitudinal directions as the other as the M5, the other stack of M5 brings, but they extend in fibers inside this cotangent bundle. Okay, and this will give rise to punctures because they are fibers who's located at a special point on C. They give rise to punctures that on this Riemann surface C. Okay, and this will enrich the resulting 4D theory that you get by compactification. Okay. So with this kind of Brink setup, you can because of the non-compact ambient space, you can take a limit to decouple gravity, and then you end up with 2,0 theory coming from this M5 brings on this flat space times the Riemann surface C. Okay, but potentially with punctures that's coming from this defect M5 brings. Okay. I should have emphasized that when on this geometry, if you think about the SO5 R symmetry of the M5 brings as generated by the transverse directions to this 6 directions, on this ambient space geometry, this 5 directions are split into 2 plus 3, where the 2 directions are inside here, essentially identify with the symmetry on the tangent bundle of C, and the SU2 R symmetry, SO3 R symmetry rotates this other 3 directions. Okay, and this translates into the 2,0 theory to preserve supersymmetry. This translates into 2,0 theory as a certain topological twist, a partial topological twist that you need to do to preserve a residual of the supercharges upon compactification. Okay, this partial topological twist can be thought of as identifying the SU2 structure group on the tangent bundle with the diagonal subgroup of SO2 times the SO2 R symmetry. Okay. This SO2 R symmetry coming from this splitting. So once you have done this twist, the original 5 scalar fields in the 2,0 theory that parameterize excitations in the 5 transverse directions to this M5 brings, the split into 2 and 3. 2 complex scalars after the twist form a holomorphic 1 form and its conjugate. This is sometimes referred to as the Higgs field, not to be confused with Higgs branch, sometimes referred to as Higgs field. And the other 3 scalars are labeled by 3, 4, 5. Okay, any questions?
Is the Higgs field independent of the 4 directions of R4?
All these fields can in principle depend on the other directions. The space-time directions, and this will be important.
They all depend on all 6 directions of the 62,0 theory.
They depend on the 4 directions. So these are they could all depend on all these directions, all 6 directions. Yes. But their dependence on this C on the next slide will be determined by some supersymmetry equations.
Oh, okay. Thank you.
Yeah. Okay. All right.
Sorry, I don't understand the difference between the left side of this slide and the right side. One of them is a 60 theory on sigma, the other one is on C. But what's the relation?
Yeah, so the main difference is that on the left, I'm talking about a realization of the effective theory. So here I'm talking about the rank 1 case. The effective theory of 4D2 SCFT on the Coulomb branch realized from a 60 free 2,0 theory reduced on the Cyber-Witten curve. On the right-hand side, I'm giving you the UV description of the SCFT directly as a 60 interacting theory reduced on a different Riemann surface known as the UV curve. And this, in the low energy limit, will give rise to the 60 theory that I described on this side.
I see. Okay. Thanks.
So this is what I meant by a UV complete description.
Mm-hmm.
So on this side, I'm talking about the IR description and the 60 lift. Here, I'm talking about directly the lift of the CFT.
Can you say how is it that the 62,0 interacting theory flow to 60 U1?
So the idea is, so this is discussed in quite detail in Witten's paper. This solving four-dimensional theory using M theory. But the rough idea is that so you have a stack of M5 branes, right, that wrap the C, and because of the dynamics, the kind of the curvature of the C and also the punctures, these branes can join and split. So in the end, it will become a single M5 brane.
I see. Thank you.
In the IR. Mm-hmm. Okay, so let's continue. So as was asked just now, so this fields potentially can depend on 6 directions. So here I'll mostly focus on the Higgs field, but the idea is that you can obtain the modular space of the resulting 4D theory that coming from this compactification by solving certain supersymmetric BPS equations. Okay, and this BPS equations will determine the dependence of these fields on the space-time coordinates. And if these solutions manifestly preserve the U1R symmetry, okay, then we expect to obtain a 4D into 2 SCFT as opposed to just a general quantum field theory. Okay. All right. So now we want to make this picture more precise, meaning how we can recover the effective theory from or this 4D description, okay, from this 62,0 competitive on the UV curve, or in other words, the class S description. And this in general uses involves the so-called Hitching system. Okay, so here I just want to emphasize that the quantum Coulomb branch geometry, which I emphasized last time, received contribution from integrated on massive particles. Okay, so the pre-potential is non-trivial. It's not just quadratic. And if you want to honest compute it, you have to take into account various instantaneous contributions. But here I will tell you a method that obtains this from solving some classical equations that describe the Hitching system. So where does the Hitching system comes about? To see that, we need to compactify the theories, this theory on one additional circle. So suppose we put the 2,0 theory on this on another circle S1 in the 4 directions, which are going to be the space-time directions of the would-be 4D2 theory. Okay. And depending on the order of compactification, we have 2 different sequence of theories. Okay. So if we first compactify on the Riemann surface C, as I described, you will get 14/2 superconformal field theory on this R2, 1 times S1. You just inherit this actual circle. And if you compactify on the circle, you get some 3D/4 theory on this flat space R2, 1. But you can also carry out the procedure in a different order. You first compactify on S1. So as mentioned in the first slide, that will give rise to a maximal super-Yang-Mills theory in 5 dimensions. And we will also inherit this UV curve C. Okay? And if you reduce the 5D theory on the UV curve, you by consistency, you should recover the same 3D/4 theory. Okay. But what's important here is that although these 2 compactification will give the same theory, there's a non-trivial map between the RG flows. Okay? In some sense, they're related by a mirror symmetry. Okay? This will I'll make more precise. Okay? But then the question of sorry. But then the question is what is the Coulomb branch of this theory can be answered as follows. The Coulomb branch of this theory would reduce after circle reduction will enhance to the Coulomb branch of the 3D/4 theory. It becomes 2 times the dimensional gets enhanced, but the Coulomb branch of the theory will be inherited here. Okay, the enhancement is coming from line operators wrapping this circle. But you can describe the Coulomb branch here using the by studying this 5D theory on this Riemann surface. Okay, because that's supposed to give rise to the same theory. And the 5D theory reduced on the Riemann surface, the supersymmetric configurations of that is described by the Hitching equations. Okay, so F is the field strength of the 5D gauge fields, and phi are the Higgs field, which I have told you about here. Okay, it's a part of the vector scalars in the vector multiplet of 5D into 2 super-Yang-Mills theory. And this equations describes the Higgs branch of the 5D theory, C. Okay, and if you do this compactification, this will give rise to the Higgs branch of the 3D interval theory in this particular description. But as I mentioned, there's a mirror map between these two RG flow. So the Coulomb branch here will just be given by the Higgs branch here. Okay. So just to make these words into a more concrete diagram, the idea is that the Higgs branch of the 5D theory reduced on the Riemann surface is described by the solution to the Hitching equations. Okay, this is the so-called Hitching moduli space. And by mirror symmetry, that will be related to the 3D Coulomb branch that's coming from this RG flow. And that's closely related to the Coulomb branch of the 4D theory. And more precisely, the relation is given by a certain projection map, which here is schematically speaking, coming from dropping the holonomies that arise from, that are kind of enhanced the Coulomb branch directions coming from this compact circle where you reduce IS1. And more precisely, this is given by this structure of the Hitching moduli space as a non-trivial fibration over a special Kähler manifold known as the Hitching base. Okay, and this Hitching base can be also directly obtained from the Higgs field as holomorphic sections of this gauge invariant combinations of the Higgs field. Okay. So okay, so in the end, the Coulomb branch of the 4D theory through this procedure is just given by the Hitching base. So I want to emphasize again that these are solutions to classical equations. Okay, so if you remember, I started by talking about a Lagrangian, and I told you that solving classical equation motions doesn't give you the exact Coulomb branch, doesn't give you the exact pre-potential. You have to take into account instanton effects. But here, I've told you that somehow the Coulomb branch of the 4-dimension theory is exactly given by solving some classical equations, although they are more complicated. Okay? And where's the magic? The magic is coming from this mirror symmetry. Okay, as I emphasized before, the Higgs branch is typically much more protected than the Coulomb branch. And because there's a mirror symmetry that relates the Coulomb branch of one RG flow to the Higgs branch of the other RG flow, this is what makes it possible to represent the 4D Coulomb branch as some base of some modular space coming from solving classical equations. Okay. So this you probably have seen elsewhere as well in the context of 2D mirror symmetry. All right. Okay, so I've told you how to recover the Coulomb branch geometry from this Hitching system. What about the subwidden curve that somebody asked on the last slide? Okay. The subwidden curve can be described as follows. So if you take the following holomorphic coordinates for this cotangent bundle, so z is the holomorphic coordinates on the UV curve C, and x parameterize this cotangent direction. Okay, and in that direction, in that description, the subwidden curve is simply given by the so-called spectral curve, okay, which is another curve inside this cotangent space that is a branch cover over the UV curve. And it's described by a solution to this equation. Okay. And the subwidden differential in this procedure is just given by this simple holomorphic differential. Okay. So I mentioned that you can make the class S construction much more interesting by include punctures. So how do we describe these punctures in terms of the Higgs field? So the Higgs field, so far, I assume to have no singularities. For example, here I'm assuming there's no singularities. Otherwise, this equation, teaching equation gets modified. But you can introduce singularities for the Higgs field on this UV curve C. Okay? And these are known as punctures. Or if you like the superconformal field theory language, this corresponds to codimension 2 superconformal defects in the 2,0 theory. Because we want to construct, so these punctures can be quite general. So you can use this puncture to construct non-conformal for the quantum field theories, include two quantum field theories. But here we're interested in superconformal field theories, and that puts some constraints on the punctures. So in particular, the puncture should obey the U1R symmetry invariance. Okay, and I leave it as an exercise for you to check that such punctures will have to take this form. Okay, in particular, this coefficient matrix is nilpotent. Okay, so the rough idea is that this by itself doesn't look U1R invariant, but there's a gauge transformation that you can do. An SU gauge transformation here because we're talking about the A1 2,0 theory. And to restore its form after you perform a U1R rotation. So whenever you talk about gauge transformation, you should have in mind doing that in either the 5D description or the 3D description, because there's no such gauge symmetry. There's no such ordinary gauge symmetry in the 2,0 description. So one important thing that the punctures introduces are extra flavor symmetries. Okay. This flavor symmetries can manifest itself as a mass deformation of the theory. The mass deformation will break the superconformal symmetry, and in particular, it will modify the singularity of the Higgs field as follows, introducing some semi-simple elements. Okay, these are the mass parameter. For example, here associated with the SU2 flavor symmetry. Okay. Now, with this punctures in hand, you can combine you can put them into the class S construction to construct general conformal field theories. So the simplest thing that you can construct is to start with the case when the UV curve is a sphere, okay, and you can introduce a bunch of this so-called simple punctures in the one case. There's no difference between, but in the general class S setup, there will be other punctures, which I'll talk about shortly. But in this case, you just have the simple punctures. And just from the singular behavior, sorry, just from the singular behavior that you require for this Higgs field around all these different punctures, with a polar matrix that determined by these mass parameters, as well as the form of the spectral curve, you can fix the subweighting curve to be of this form. So in this construction, subweighting curve is the same as the spectral curve. And where this coefficient is going to be some polynomial of degree 2 and with a non-zero constant term. And this is fixed by requiring this phi to behave as you expect at all these three punctures, here located at 0, 1, infinity, when I write them as this. Okay. In particular, I leave it as exercise to you, but you can check that this, sorry. This polynomial will only depend on m. There's no room for extra parameter that would correspond to a Coulomb branch parameter. So in this sense, that this theory is rigid. Okay. This theory, the resulting the class S construction gave you a rigid theory with no Coulomb branch deformation, and that's no surprise because this actually corresponds to the corresponds to the tri-fundamental hyper. Okay, so in other words, if you like, it's a doublet of it's a doublet SU2 doublet of the usual hypermultiplets. Okay, but you can make it more interesting by including a more general set of punctures. For example, if you have 4 punctures, okay, of the same type, you can work out the subordinate curve following the same procedure, and this will give rise to the so-called subordinating theory. which is SU2 plus 4 fundamental hypers. Can be represented by this quiver diagram. Why do I write this quiver diagram as opposed to this? Okay, to represent the same theory. It's because you can take a limit. You can take a factorization limit of this Riemann surface. So this Riemann surface has some compact structure moduli that are labeled by Q, which is essentially the location of one of the punctures. If you fix the other punctures to be at 0, 1, infinity, this extra location, this fourth location, will be a complex structure moduli of this punctured Riemann surface, punctured Riemann sphere. And by tuning this parameter, you can get to different frames where this Riemann surface factorize. So, for example, if you pull this puncture close to the puncture at 0, you get this factorization. If you pull this puncture close to 1, you get this factorization. Okay. This will correspond to different SURD frame of the same theory. Okay, where the mass parameter gets exchanged. And in this, in either of this SURD frame, because each puncture corresponds to SU2 doublet of hypermultiplets, so naturally you get this quiver. Okay, so the cylinder will represent the SU2 vector multiplet, and that's the gauge group here. And each 3-puncture sphere will correspond to a SU2 doublet of hypermultiplets. That's being gauged here. So as I mentioned briefly, you can generalize the story in several ways. First of all, so far we focused on the description, the simplest case, description in terms of the A1 2,0 theory, compactifying the Riemann surface with punctures. But you can consider more general 2,0 theory of the AD type, compactifying the Riemann surface, okay, with multiple conformal punctures. And in this more general setup, these punctures will be labeled by nilpotent orbits of G. Okay. In the A1 case, there's a single type, but in general, there is a much richer structure. There's also relation between different punctures by Higgsing, and this is more general punctures are described in this paper. Okay, and once again, the semi-simple elements associated with these polar matrices in this general 2,0 case will correspond to mass deformations of the CFT.
Question.
There's some question?
Yeah. Does picture shed any light on global structure of the flavor symmetry group?
Which picture?
The general Guyotto curve picture, I guess. That's the
let's
question.
See. That's a good question. I guess that will be related to the representation. So that will be related to the representation which you use to define the spectral curve. So in principle, you can write the spectral curve when you. So the determinant is so you first need to pick a representation. So all these things these are valued in Lie algebra of the ADE type. And when you take a determinant, what you should do is you take a particular representation of the ADE Lie algebra, and you take a determinant in that matrix representation. So in principle, I guess the global structures can manifest itself if you consider different representations. Although I'm not sure if that has been studied. That's a good question.
I think the more general point is that there's additional information based on spectrum of line operators you can write down, and that can constrain the structure of the global symmetry group.
That's also true, yes.
And so usually, I guess now it's called defect group or things like that. So you actually have some choices sometimes about what spectrum of line operators you wish to retain.
Right. That's right. But that should be related to the choice of the spectral curve, I suppose.
Right.
Yeah.
It's also related indirectly to the choice of what sections of fibrations and choice of representation data you pick.
Right.
So it is related to Mordell-Weil data.
Right.
Okay. So it would probably also depend on the choice of 6D partition function.
Yeah.
Correct. That's the same point as talking about the defect group.
That's right.
Right.
Yeah. Thanks for the question and comments. All right, so I just mentioned one possible generalization. So let me give you some example. So one example is the realization of one of the most basic four-dimensional into two superconformal field theory, which also has a Lagrangian description as the conformal QCD, namely SUN super-Yamil's theory coupled to 2n fundamental hypermultiplets. This theory has a simple class S description in terms of, again, a sphere as your UV curve with 4 punctures. 2 of the punctures are the so-called simple punctures, which are closely related to this simple punctures in SU2 case. But there are also 2 other punctures which are full punctures. These are punctures that carry these simple punctures they're simple because they're simple in the sense that they carry the minimal of flavor symmetry U1, and these full punctures instead carry the SUN flavor symmetry. Okay, and more generally, you can also construct from the class S construction. You can also construct many superconformal field theory that do not necessarily have Lagrangian description. Famously, the TN theory is constructed by, again, taking the simple UV curve, the sphere, but with 3 full punctures. Okay, and in this case, you get the interacting CFT that does not have the Lagrangian description, but with this global symmetry group. Okay. So one general criterion for having a Lagrangian description is for your Riemann surface to have some moduli, some complex moduli, which is the case when you have 4 punctures, but not the case when you have 3 punctures. And you can further generalize this class S construction by including more general punctures. So far, the punctures that we have encountered are of the tame type. These are punctures where the pole of the Higgs field is simple. But there are also punctures where the poles can be of higher order. It can also be of the fractional order. Okay. These are explored in various papers here. And in most of these cases, the U1 R symmetry or conformal symmetry will be emergent. So you should think about this more general punctures as defining some UV description of the codimension 2 defects in 2,0 theory that flows to some superconformal codimension 2 defect in IR. Okay, that engineer this conformal punctures. And these punctures are crucial to realize this Argyros-Douglas type theories with fractional scaling dimension on the Coulomb branch within the class S setup. Okay, all this tame punctures, class S setup construct from tame punctures necessarily give you 40 SCFTs where the Coulomb branch spectrum have integral scaling dimensions. Okay. So let me just give you. Yes.
You found there's a paper by Chris Beam this year, and his collaborator, and they actually construct Argyros-Douglas type theories from A2 theories, twisted A2 theories, but with simple, but with tame punctures.
But the scaling dimension is at most half integral.
That I'm not sure about, but they claim that they can construct more complicated Argyros-Douglas theories by studying twisted A2n for higher values of n.
Yeah, so I'm aware of the paper, but to be honest, I haven't read it. But my expectation is that you can not get theories with general fractional scaling dimensions. You can probably get half integral, but not more. Just from
what would be the reason behind that?
Oh, it's just from the okay. So there's a technical reason. Is that in the class S construction, this how should I say it? This z coordinate, when you take the scaling limit using the tame punctures, this z coordinates always have 0 R charge. Okay, the phi has U1 R charge 1, and this coefficient will have U1 R charge 1, and the z will always have 0 R charge. And because of this, the structure of this singularity only involves things with integral R charge. The Coulomb branch operators that you get always have integral R charge.
I see. And you said that it can change to half because with twists you might get.
Yeah, that's right.
Okay,
so I should emphasize. Yeah, I should emphasize the. So as I mentioned, the Coulomb branch is parameterized by the holomorphic sections of this this holomorphic functions, which are coming from trace of this Higgs field to some power. And if the Higgs field contains things which are only have integral R charge, necessarily you only expect integral R charge in the Coulomb branch spectrum. So that's the technical thing that leads to this conclusion. Right.
I see. Thank you.
Yeah, no problem. But if you start allowing this Z, if there's some scaling limit where the Z start to have also have a U1 R charge in that scaling limit, then this guy can have fractional R charge because phi will have R charge 1, and this is how you can get this fractional scaling dimensions using these wild functors. So let me just give you two quick examples. There's lots of references here. Let me just give you 2 examples to illustrate how you can recover this Archer-Douglas type CFTs from class S constructions with irregular puncture. The simplest type is this A1, A2 CFT, which is rank 1, has a Coulomb branch operator of dimension 6/5, so it's of the fractional type. Just going down. The class S construction of this theory is given by the A1 2,0 theory on the UV curve, which is a simple, which is just a sphere, with a single puncture. It's a single puncture with the coefficient, with the pole that's fractional. Okay, and following the same procedure discussed here, you can figure out the separating curve and separating differential. And you find that it matches with the result you expect from the Coulomb branch analysis of, say, SU2 with 1 flavor or SU3, a pure superamines on the Coulomb branch. Okay, and this irregular punctures also allow you to construct familiar theories that you already have class S construction, but they will buy you some. It will give a more give a more manifest picture of many, will make manifest many physical features of this theory. So the particular example that I just want to mention is the familiar 4D into 4 superamines, okay, with SU2 gauge group. So this or in other words, this more precisely is into the star deformation, can be realized by A1 2,0 theory on a UV curve, which is a torus with a simple puncture. Okay, where the puncture is of this again the tame or regular type, where this coefficient parameterizes the mass deformation. Okay, but this theory. So I didn't say this before, but this simple punctures make manifest only a U1 symmetry, but it's enhanced to SU2, as you can check for the into 4 theory thought of as an into 2 theory. So the into 4 theory as an into 2 conformal field theory has SU2 flavor symmetry, and the into 4 language it becomes part of the SO6R symmetry. And moreover, this SU2 also has a Witten anomaly. Okay, this is the Tohoff type with an anomaly associated with flavor symmetry. It's not an inconsistency of the theory, but it's a feature of the theory. But this kind of feature of the important feature of the 4D theory is not manifest in this picture. First, the SU2 is coming from enhancement. That's not clear from the picture. Second, the Witten anomaly is completely obscure from this picture. Okay, but this can be made manifest in the generalized class S construction with irregular punctures. Okay, so in this particular class S construction, what you have, you start from the A2 2,0 theory, but with the alter automorphism twist that I think Ali already mentioned, that was used in different contexts. In that case, you have 2 punctures, 1 irregular punctures and 1 regular puncture. They're both twisted, so in a sense they're connected by some Z2 twist line. That's the alter automorphism Z2 of A2 Lie algebra. And again, this irregular puncture is characterized by a simple singularity, but the singularity has this fractional pole. Okay, and again, following the same procedure to work on the Seiberg-Witten curve and work out the spectrum, and that tells you that it's the same as the interforce preammules. But in this picture, this regular puncture would, because it's a twisted puncture from the A2 or SU3 theory, from the general discussion of these authors, the invariant subgroup of SU3, which is given by this SU2, manifestly describes the flavor symmetry of this interval theory. And as explained in this paper, the fact that it's a twisted puncture of this from the A2 type also makes manifest that it has a Witten anomaly. Okay, so I just want to say that given a folding includes two theory, there are various constructions you can obtain from class S from different Riemann surface, different punctures. But some construction will make manifest some features and some will not. So there's a choice that one can make to more effectively extract the dynamics.
Sorry, do you know that this USP2 flavor symmetry has Witten anomaly because you know that the corresponding SCFT is n equals 4 SU2 Yang-Mills, which has a Witten anomaly in its SU2? So
if you know nothing about this puncture, that's one way you get some intuition. But we can actually argue that this puncture independently always carries a Witten anomaly. So in other words, any class S theory that you construct that involve this twisted A2N punctures will always have a Witten anomaly associated with the USP group that's coming from the invariant subgroup.
I see, but to learn that it necessarily has Witten anomaly, what's the argument?
So they explain in this paper. So there's an argument that deform this. So if you consider this puncture with some other puncture, you can deform the theory such that in IR becomes some gauge theory, and you can explicitly check that in that gauge theory there's a Witten anomaly.
Okay, I see. Thank you.
SO type, yeah, SO type gauge theory with USP type. SO2n plus 1 type gauge theory with USP type flavor symmetry with Witten anomaly. Yes.
Thank you.
Yifan?
Yes.
Is there a distinction between the two theories in terms of the line operators or generally extended operators that exist for them?
That's a very good question. The short answer is I don't know. There could be. So this is related to the earlier question. Yeah. So far I'm being agnostic about this extra discrete discrepancies. That's a good question. So here, all I'm claiming is that subwooden geometry with the deformations, the general deformations are the same, derived from this UV description or from this UV description. But you're right that if you keep track of the spectrum lines, they could differ. Okay, there's some question in the chat. Or just comments?
Yeah, it's a question about other ways to see accidental flavor symmetry enhancement.
Right. So this so indeed in many cases the symmetry enhancement can be seen from going from the the class S construction with regular punctures to irregular punctures, but this is not always possible. It happens in many cases, but it's not always possible.
Yeah. As pointed out in chat, also one way to do it is to compute properties of the operator spectrum.
Yeah, you can certainly also compute that's right. That's right. Yeah. Okay. All right. So that's all I'm going to talk about the class S construction. You can, if you want to know more, you can ask me later. But let me now move on to the other construction that I promised I'll talk about. That is coming from type 2B probing some threefold singularities. Okay. So why do you want to consider type 2B on Calabi-Yau threefold singularities? As I emphasized in the previous lectures, the 4D unit 2 Coulomb branch is essentially described just by a spectral geometry. Okay. So in the sense that the Coulomb branch itself is a special Kähler manifold where the prepotential is completely, the prepotential completely determine the dynamics on the Coulomb branch. Okay. But now you remember, special geometry comes naturally from the moduli space of Calabi-Yau threefolds, that you may remember from studying 2D CFTs or coming from computation of type 2B string theory on compact Calabi-Yau threefold. Okay, so then one can actually imagine that this could be the Calabi-Yau threefold will be an arena to construct 4D 2 CFTs by taking some decoupling limit where you can decouple gravity. Okay, so that's why we're going to consider type 2B, four space-time directions times some Calabi-Yau threefold. The requirement of 4D 2 supersymmetry tells you that this transverse direction had to be Calabi-Yau, satisfy the Calabi-Yau condition. So we admit some Kenney spinors, now finish the 4D 2 supersymmetry, and because we want to decouple gravity, so we need to take this Calabi-Yau manifold to be non-compact, such that the effective Newton's constant goes to 0. And in addition, because we want to construct superconformal theories in 4 dimensions, leave on this space-time directions, we need to require this Calabi-Yau manifold to have an extra C-star action. Okay? So in the field theory, that corresponds to a combination of a scale transformation as well as some U1R rotation. Okay, it's part of the superconformal symmetry in the group 2 theory. And this kind of constraint basically tells you, along with the this non-compact condition, tells you that there is some isolated conic singularity, the threefold singularity. And there have been lots of works on this, giving you a couple of the references here. Okay. All right. So in the rest of this lecture, we'll focus on a particular class of such isolated singularities, which are very simple. They're described by some hypersurface hypersurface singularities. So in other words, there are some equation with 4 complex variables that determines singularity that sits in C4. Okay, and the fact that we want to be isolated, it means that suppose the singularity is located at the origin. That means that this function as well as its first derivative vanish at the same point. Okay. And then the requirement of a C-star symmetry, a scaling symmetry, says that there's a set of charges Qi that you can assign to these coordinates xi, such that when you do a C-star transformation on the coordinates, the polynomial itself scales by an overall factor. The fact that the requirement that this Calabi-Yau has a conic metric, has a Calabi-Yau metric. Sorry, this singularity has a Calabi-Yau conic metric, says that this C-star charges have to satisfy this inequality. Okay, so by now you probably have remembered that to describe this describe the Coulomb branch of the 4D2, all you need to know is something like a subwooden differential and a subwooden curve. Okay, or in other words, some special coordinates. Okay, that's coming from integral of the subwooden differential along cycles on the subwooden curve. So what plays role of the subwooden differential here in the type 3 setup? That role is played by some instead of a meromorphic 1 form, it's played by some holomorphic 3 form. Okay, which can be written as follows. Okay, so if you don't like this notation, this means that it's roughly speaking dx2 wedge dx3 wedge dx4, where the denominator is given by the partial derivative of this polynomial with respect to x1. So this is the way to write this that's valid everywhere on the singularity. Okay. And here I've also included potential deformations of the singularity coming from the compact structure deformations, which are parameters by U alpha, which will be related to the Coulomb branch parameters that will be that we will explain shortly. BPS particles in the 4D2 theory that's coming from this compactification will correspond to D3 brings, okay, which are the fundamental objects in type 2 string theory. And because they're BPS, the D3 brings are calibrated in the sense that they have to wrap special Lagrangian cycles on the deformed singularity. And the mass of this BPS particles will be determined by the center charge, which is given by the integral of this holomorphic free form over some Lagrangian cycles, which I'll label by C. Not to be confused with the UV curve from class S construction. And then the Coulomb branch operators, more precisely the VEV of these Coulomb branch operators, which are labeled by U alpha, as well as some mass deformations and chiral couplings, which all parameterize deformation of the Coulomb branch EFD, has a explicit description in terms of the type 2B geometry. So in particular, in the type 2B geometry, you have this complex structure deformations, okay, which are take the following form. So each term is like a monomial in the variables xi, and with some coefficients which you can tune, okay. And depending on the scaling dimension of this coefficients, or the R charge of these coefficients, once we specify, it will correspond to either Coulomb branch operators or mass parameters or chiral couplings. Okay? So how do we fix the U1 R charge of these coefficients? The way you fix them is by normalize the R charge such that the holomorphic 3 form has R charge 1. Why is that? Is because the integral of the holomorphic 3 form over 3 cycles give rise to center charge. And I emphasized in the first talk, importantly, the center charge, the complex center charge carries U1 R charge 1 in this normalization. Okay? And this sets the R charge, U1 R charge of the holomorphic 3 form. And then requiring this Q to be proportional to the actual U1 R charge up to a constant alpha hat. Okay. This may be confusing, so let me put a bracket. So the Ri are the actual R charge of the xi coordinates. Okay. And requiring these conditions, you can fix and the form of this omega. Okay. You can fix the proportionality constant to be this ratio. Okay, and importantly, the condition that this is positive tells you that this is positive. Okay? So in some sense, that this existence of the Calabi-Conic metric is related to a notion of unitarity in the resulting 4D include 2 theory. Okay, and then the way you can decide which of these parameters are Coulomb branch VEVs or mass parameters or chiral coupling is to look at their R charges. For example, if the R charge is bigger than 1, they satisfy the unitarity required for a Coulomb branch operator. They correspond to a Coulomb branch operator. If it's equal to 1, it corresponds to a mass parameter, the same as the dimension of the mass parameter. And if it's smaller than 1, it corresponds to chiral couplings, which are couplings you can pair with the Coulomb branch operators to generate the 4D include 2 preserving deformation of the CFD. Okay, so let me give you a concrete example. So let's go back to this favorite example again, the A1, A2, namely the simplest Archer-Stoklas theory, the rank 1 Archer-Stoklas theory with no flavor symmetry and a Coulomb branch VEV of dimension, a Coulomb branch operator of scaling dimension 6/5. In that context, the relevant singularity is described by this following polynomial. Okay, so this is so A1, A2 here means that this part of the polynomial corresponds to the polynomial that defines the A1 singularity, and this corresponds to the one that defines the A2 singularity. Okay, and you can easily figure out the C star charge of the singularity, and it's going to be this this list. And from this general description of normalization of the holomorphic 3 form, you can fix the proportionality constant between the C star charge and the extra U1 R charge. It's this combination. Okay, and this will be the extra R charges of the coordinates. And then you can study general deformations of this singularity defined by this polynomial, and the coefficient. So because these are quadratic, there's no non-trivial deformations that you can. There's no non-trivial deformations, but for this cubic polynomial, there are trivial. For the cubic polynomial, there's non-trivial deformations that are coming from the linear term in X4 and also the constant. And there you can figure out the scaling dimension of these coefficients by remembering that this polynomial itself has R charge has a C star charge 1, and you know the R charge of this individual coordinates here. And from this analysis, you see that this coefficient corresponds to the Coulomb branch operator in this resulting Fording two theory because it has scaling dimension 6/5. And this lambda coefficient multiplying x4 is precisely the Cairo coupling. Okay? That has dimension 4/5. So because x4 has dimension 2/5. Okay, 4/5 to power 2/5 is 6/5. Okay, and you can also compute the conformal center charges for this theory, starting from this description. Okay, so this is some general formula that was described in the paper from Shapir and Tajikawa, which I mentioned in the previous talk. And I leave it as an exercise to show that this formula will give you the desired center charges that you know from that you can look up in the paper from say Philip and Mattoni and friends. Philip and Mario Mattoni and friends. Okay, but to carry out this procedure in this from this threefold singularity, I need to tell you what is RA and RB. So RA turns out is completely determined by the spectrum of the scaling dimension of the Coulomb branch operators, or the U1 R charges from this combination, and RB is completely determined by, again, this alpha hat, which is related to this proportionality constant between the C star charge and U1 R charge, and the mu, which essentially counts the number of this parameters. Okay, this is also known as the Miller number associated with singularity that counts the number of. So this is singularity. Once you deform it, generally it will give you it becomes like a bouquet of 3 spheres, and this Miller number essentially counts the number of spheres. Okay, and for the particular case of A1, A2, this Miller number is equal to 2. And with this information and this formula, you should be able to recover this. So
sorry to interrupt, Eric. A couple of questions in chat. Do we know which Calabi-Yau is the mirror of this one? And can we think of these singularities as collisions of conifolds?
That's a good question. That's a good question. Well, let's see. So the first question, which Calabi-Yau is a mirror to this one? I have to say I don't remember, but I think it's discussed in one of the papers from Clan, Vafa, and collaborators. It must be discovered somewhere. For the second question, that sounds reasonable, but I'm not sure if that has been worked out.
Yeah, I'm also not sure if anyone in chat knows the reference. Feel free to add it.
Yeah, these are good questions. Thank you. Okay. So I've told you about this type 2B construction, and this I've told you about the class S construction, also type 2 construction. So you may wonder what are the relation between them. Okay. In general, this relation is murky. I think this is also partly related to Federico's question, the first question. Okay. But for the particular case, when the threefold singularity is described by of the A comma G type. So in those cases, it can be described by some locally by a vibration of an AN type singularity over over a curve, okay, with the coordinates given by Z. In that case, you can perform a T-duality in the AN singularity direction. So there's a U1 isometry for the AN singularity, and you can do a T-duality in that direction. And from general argument, you know that they give rise to NS5 brings now in type 2A. And if you further take the low engine limit and lift to M theory, that will give rise to the class S construction of the AN minus 1 to comma 0 theory on this Riemann surface, described by this locally by this coordinate Z. Okay. So, but this is the relation that only works in this very special case. Okay. So the general picture you should keep in mind from this discussion of this construction is that the Calabi-Yau singularity engineers a large class of Fording two theories. The class S construction also engineers a large class of Fording two theories. They intersect as sometimes they construct the same theory, but most of the cases they construct distinct theories. well, it could be that our understanding of this class S construction, possible class S construction or possible Clavier construction is also incomplete. So the overlapping region can be bigger. I should also emphasize there are many other constructions of this top-down constructions of this 14.2 theories coming from S-fold in this nice paper by Fabio, Sakura, and collaborators, and also this potentially from T-brains where there's a non-trivial supersymmetry enhancement from the work of Federico and friends. Okay. There's a question. There's a comment. Yes. So if there are so there's a comment. If you have massless hypers along the Coulomb branch, the formula is missing this contribution. Yes. So it turns out that for this threefold cases, there's always no free hypers. That's why this will be the full answer. So this part, I think what Michele was saying, that this part is coming from the free vectors on the Coulomb branch, but there's no extra free hyper contribution. That's a feature of this threefold constructions. But in general, you should include also contribution from free hypers. That's included in the original paper of Shapir and Tachikawa. There's another question. The mirror map is non-trivial for Clavier encoding 5D into 1. Does mirror map become trivial? Not sure what the question is referring to. The mirror map is generally non-trivial for the 4D into 2. Do they always have to be polynomial? There are polynomial in this for the hypersurface singularities. Yes, there's some general discussion by Milner and also by Arnaud. But if you consider some singularities, this isolated conic singularity, which is not a hypersurface, the deformation story is much more difficult. Okay. All right, so let me now move. Okay, so this is how I'm going to talk about 14 into 2. There will be some open question I'll mention in the end, but let me now briefly talk about 5D into 1. Okay. All right. Okay, so let's now switch gear to talk about some aspects of 5D into 1. Okay, so the 5D superconformal field theory are kind of funny in the sense that there's the maximal supersymmetry allowed doesn't have a superconformal version. The only possibility for a supersymmetric conformal theory in 5 dimensions would have to have into-1 supersymmetry, and that's contained in this superconformal algebra F4. Okay? The Bosonic subalgebra is given by the conformal group SO5, 2, and SU2 R symmetry. If you remember, the R symmetry for into-2 super Mills theory in 5 dimension would be SO5R, but that's being compatible with embedding into a superconformal group. Okay. So in this 4D discussion, I remember that so in this 5D discussion today, we'll again take this EFT approach that is sort of like bottom up. And in the next lecture, and also in Fabio's lecture this afternoon, you will hear about the more top-down approach to this 5D CFT coming from brain construction as well as from geometry constructions. And from this bottom-up approach, we want to study the EFT and recall that in the 4D NG2 context, there are two different ways we can use to construct the CFTs from the 4D Lagrangian. One way is very simple. It's just the case when the 4D Lagrangian has manifest conformal invariance that's obtained by conformal gauging of some hypermultiplets matter. And in some other cases, you can also identify the CFT from a non-trivial RG flow, where you can pinpoint where the CFT is on the Coulomb branch by studying the effective theory. There are some Argyros-Stoklas points. Generally, there are some Argyros-Stoklas points on the Coulomb branch of this asymptotically free gauge theories. But now in 5D, the story is quite different. As Fabio already mentioned, and Kantaro also mentioned last week, it's not possible to have manifest conformal invariance. It's because in 5D gauge theories, some other question? There's no instanton correction for mirror map. Yeah, maybe we can discuss it later. I'm not sure what the question is referring to. Okay, maybe let me continue and we can come to that in the discussion, if that's okay. Okay. Yeah, so as was already mentioned, I guess in Fabio's talk, the 5D Yamil's coupling 1 over G squared has dimension of the mass. So the gauge coupling is irrelevant, and I mean classically irrelevant. So there's no way to make a non-trivial conformal interaction with gauge fields. You can, of course, you can do it with hypers, but it will not be interacting in my strict sense here. But one still can ask whether one can construct or identify some CFT points using the EFT approach. Okay, and here there's a lot of similarity with the 4D story in the sense that the field content of this basic multiplets in the 5D EFT is essentially the same as that of the 4D 2 because they share the same number of point gray supercharges. Okay, just organized a little differently for the vector multiplet. And the idea, again, will be to look for a fixed point on the moduli space, okay? And because it's going to be a CFT, so any scale has to go away. So in particular, any gauge coupling in the EFT that describe interaction between the 5D photon fields has to go to infinity, okay? So that this mass scale like parameter goes to 0. This means that we should look for some strongly coupled UV fixed point from the EFT perspective. Okay, so this connection between this 5D EFT and this 5D EFT and this the superconformal theory can also be understood as follows. So if your 5D into 1 theory has some relevant deformations upon which you have a 5D into 1 effective theory that's described by vector multiplets coupled to hypermultiplets, like the 5D into 1 gauge theory. This means that there's a relevant parameter, which is given by the 1 over GMU squared, which has mass dimension 1, and the CFT point is located at the origin of the Coulomb branch, parameterized by the vector multiplet, as well as the strongly coupled point. But you can also look at in the other way, where this mass dimension 1 deformation 1 over GMU squared correspond to into 1 mass deformation generated by a generated by a BPS operator at the superconformal fixed point. But then if it's generated by a relevant operator in the BPS operator in the fixed point that couples to symmetry, coupled to a mass deformation, it tells you that this multiplet has to contain a flavor symmetry current. And then you may ask what kind of flavor symmetry is here, and this flavor symmetry in this EFT perspective will correspond to the topological U1 instanton symmetry, which is very similar to the topological symmetry that you encounter in 3D gauge theories, unitary gauge groups, for example. But here, the conserved current associated with topological U1 symmetry is the Hausch dual of F wedge F. Okay. And the operators which are charged, the operator charged under this symmetries are the corresponding instanton configurations. Okay? And the particles will just be the instanton particles, which have codimension 4, and in 5 dimension it becomes particles. And their mass are proportional to this mass scale, which is 1 over GMU squared. Okay. And because this picture typically involves turning on relevant deformation that transform under the flavor symmetry of the UV CFT, you will this RG will typically break the UV flavor symmetry. So if you go back from the gauge effective theory to the UV, typically there will be symmetry enhancement. Okay. For example, if your UV theory has a flavor symmetry G, it will be broken to this subgroup that contains the U1 topological symmetry and its commutant. Okay? And very often there's a symmetry enhancement when you want to tune to the fixed point. And there are various ways to kind of find evidence for this enhancement by computing, for example, supersymmetric indices and the supersymmetric boundary functions, and more general supersymmetric boundary functions. And also study the spectral instanton operators. Okay, let me just briefly mention, I already mentioned that these multiplets are in 5D into 1 are closely related to 4D into 2. Let me just list them here for to be explicit. So here you have a vector multiplet, which is very similar to the 4D case, except that the scalar now is a real as opposed to a complex. Okay, and you have the same kind of fermions in the vector multiplet. And when the scalar, the real scalar takes a non-trivial expectation value, it generates a Coulomb branch. But emphasize now it's a real Coulomb branch. It doesn't have the special structure anymore. But on the other hand, the hypermultiplets are very similar to, are more similar to the 4-dimension case. You basically have the same field content, and if the hypermultiplet has a non-trivial VEV, it gives rise to the Higgs branch, and which has a similar structure as in 4D, has a hypercator sigma model. Okay. In in 5 dimensions, you can also explore potential non-randomization theorems to constrain the effective theory on the Coulomb branch. Okay. Similar to 4 dimensions, to leading derivative order, 2 derivative order, the Coulomb branch EFT is determined by a version of prepotential that's similar to 4 dimension, but now it's a prepotential as a function of this vector multiplet or vector superfield whose bottom component is the real scalar as opposed to a complex scalar in the 4-dimensional case. And as I emphasized many times, the Higgs branch are generally protected from quantum corrections. In this case, from quantum corrections coming from gauge interactions. And they are just described by a sigma model on the hypercator manifold, essentially, in the low energy limit. But the Coulomb branch, as what happened in 4 dimensions, hosts non-trivial dynamics because the Coulomb branch effective reaction again come from integrating out massive BPS particles and potentially other more complicated massive BPS states. And there are places on the Coulomb branch where these things could become massless and the Coulomb branch description breaks down. Okay, and this leads to very rich chamfer structures on the Coulomb branch, and there are also singularities coming from various states, massive BPS states that become massless at a specific loci. Just want to emphasize the structure of the singularities in 5D is quite different from the 4D case. In the 4D, you can always go around the singularities because the singularity on the Coulomb branch are of complex codimension 1. But in 5 dimension, because the Coulomb branch is real, the singularities typically happen at walls, so you cannot really go around. Okay, this is some general thing you should keep in mind. Okay, so as I already mentioned, just from 5D supersymmetry, you can see that the Coulomb branch effective theory at 2 derivative level are just described by some prepotential that depends on this U1 vector multiplets. Okay, these are the light degrees freedom that you have after you integrate all the other method modes. And the form of the prepotential is also constrained by supersymmetry. But the supersymmetry will tell you it's a prepotential, but the form of the prepotential is constrained by gauge invariance, in particular large gauge invariance. I leave it as exercise for you to argue that the prepotential for the 5D theory can be at most cubic in this vector superfield phi I. Okay, so this superspace to make it more to make this more concrete, you can let me just tell you what this term generate through this superspace integral. So in particular, the quadratic terms will generate a Yang-Mills interaction. Well, generate a kind of abelian gauge interaction after you integrate out the superspace variables. So the usual f wedge star f. This cubic term, on the other hand, generates some new terms which you have not seen in 4D. These are the 5D transaminance term. Okay, and its coefficients are the transaminance couplings. Okay? And this is just a hint for this exercise. This is where the large gauge invariance becomes important. Okay, and just by using this constraint, that tells you that the EFT has to be at most cubic. The prepotential has to be at most cubic in the vector multiplets. You can argue that this prepotential is actually one loop exact. One way to do that is to realize the the gauge coupling 1 over the combination of gauge coupling 1 over G squared as the bottom component of a background U1 vector multiplet, and you just run the same procedure. Okay? And and from this very nice work in the 90s, combined with this non-renormalization theorem, you can completely fix this one loop potential given a matter content in the effective theory. Okay, the one loop exact prepotential takes the following form. So there are terms that are classical, the quadratic term that describe the quadratic interactions, and there's also a bare transimultaneous coupling of this type if you integrate out the superspace variable. But there are also one loop corrections coming from integrated out of massive hypers and massive vector, massive W bosons. This is from integrated out massive W boson, depending on the roots of the gauge group. And there are also one loop contribution coming from integrating out the massive hypermultiplets that depend on the weights of this individual hypermultiplet components. Okay, and these are the diagrams that you will need to extract this kind of computation results. Okay, just want to emphasize that because we have this transimultaneous coupling, there's a non-trivial constraint on the bare transimultaneous level in terms of the matter content, because the large gauge gauge invariance of the transimultaneous coupling under large U1 transformations will require the effective transimultaneous coupling to be quantized appropriately. In particular, in the case of say SUN, for SUN, a level bare transimultaneous level KB coupled to NF fundamental hypermultiplets, this effective transimultaneous level has to be integer. Okay, and I should advertise that. So here I'm focused on the effective theory from the gauge theory. Later this afternoon, you will see how this effective theory comes about from the brain construction. Okay, so since I've only started to talk about 5D, let me just give some open questions for the 4D story, which I wrapped up earlier this lecture. So I didn't really talk about this, but this is I think it's very important, which is to understand anomaly contributions coming from punctures. Okay, so this is something that's already mentioned last week during some of Cantaro's lectures, is that from the inflow mechanism, you can figure out anomalies of various coming from various brains. Okay, but one important thing is coming from the anomaly contribution from the punctures. Okay, this is explored in this very nice paper. But one could also but this work mostly focused on the perturbative type Tohoff anomaly, the part of the anomaly that's captured by the anomaly polynomial. But as Cantaro mentioned, there are also non-perturbative part of this anomaly. Okay, and it'll be interesting to figure out the contribution to this non-perturbative anomalies coming from the punctures, or in other words, coming from these defect and pi brains. And it will also be interesting to figure out potential anomalies associated with one-form symmetries. I think Ibo and the friends have some results that they will advertise in strings. And another comment I want to make, which is some kind of open question, is that there's a close relation between folding into 2 EFT and complex interval systems. Okay, this was already mentioned in the paper from Tanagi and Whitten in 1995. So the idea is like follows. So for all the examples that we know, well, from the class S construction and from the subwithin geometries that we know from the early days, there's a hidden complex interval system. Okay, what is a complex interval system? It's just roughly speaking, you can thought of as a homomorphic symplectic manifold. In our case, it will be a hyperkähler manifold, which has this fibration structure where the fibers are complex torus, which are essentially the complex space to the power n, modeled out by a lattice of full rank, so rank 2n in this case, 2r in this case, and it's a fibration over the Coulomb branch. Okay, and the complex structure of this complex torus, okay, will correspond to this effective couplings on the Coulomb branch. And as I said, this coupling essentially determines the prepotential. It's coming from holomorphic derivative of the prepotential with respect to AI and AJ. Okay, so in other words, this fibration just keep track of all the information about the Coulomb branch EFT in the 14.2 context. Why is this important? It's because the the special Kähler geometry on the general manifold has it has this it's parameterized by this symmetric. The metric is parameterized by this symmetric matrix, and for the subway for this, if you just want to describe this special Kähler geometry using elliptic fibration, because the elliptic curve only has complex structure like 3G minus 3. If the rank of the Coulomb branch is high enough, the deformational elliptic curve is not sufficient to capture the most general special Kähler geometry. So you need to consider some more general abelian variety, and this complex torus is the most general type that you should consider. Okay. And another place where this complex integrable system comes up naturally is in the context of Hessian system. So in that case, this holomorphic symplectic manifold is precisely the Hessian modular space, which I described here. Okay, and physically, that's the same as the Coulomb branch modular space of the 3D into 4 theory coming from the circle reduction of the 4D into 2 theory. Okay. But this structure of this complex integrable system is less clear in other construction of the 4D into 2 theories. For example, from Clavial 3-fold singularities, or more generally from S-fold singularities. Okay. But potentially, you can figure out this complex integral system by studying the S1 reduction of this resulting theories. And because it seems that the more general special Kähler geometries correspond to complex integral system as opposed to fibration of Riemann surface over the Coulomb branch, it will be interesting to try to classify. Well, one question will be interesting to classify what kind of complex structure, what kind of complex integral systems there are in the higher rank Coulomb branch case. And alternatively, one can also imagine that not all complex integral system give rise to special Kähler geometries that's consistent with the existence of 4D into 2 CFT at origin. Well, I'm always assuming there's a scaling limit, but even with that, you can imagine that many of this complex integral system do not actually correspond to 4D into theories. Then maybe it will be and then it will be nice to argue that maybe some very special some special criterion that we should put on complex integral system such that they correspond to 4D into 2 CFTs. Okay, I'll end there and see if there are questions.
Thank you, Yifan, for the wonderful talk. Are there questions?
Can I ask if any known examples of theories of classes are written up somewhere when the Riemann surface does not have any punctures?
You can take a higher genus.
Oh, like let's say that I compactify 62 common star theory on a genus 2 surface without any punctures.
Yeah.
What's the 4-dimensional and equals to SCFT?
I think it's like gauging. So it's like gauging two. So the idea is that you start from 3 puncture sphere and you just glue them with 3 cylinders. So it's
okay.
You see what I mean? And so you have you are gauging the 3 SUN symmetries.
Right. So this resultant theory would be independent of the particular sort of boundary conditions that we took on the punctures.
Sorry, in that case, there's no puncture, right? You just make a genus 2 Riemann.
No, but I thought that we were making this genus 2 surface by actually gluing together surfaces which will have punctures.
Right. So you are gluing 2 TN theories by gauging each SUN gauge symmetry. By gauging each pair of SUN flavor symmetry. Yes. But you have to have the SUN flavor symmetry, and the SUN flavor symmetry have to have the right flavor center chart such that is it's a conformal gauging, and that's ensured by this gluing picture here.
Right. So if for the same 3 punctured sphere, instead of taking the boundary conditions that give me a if for the same pre-punctured sphere, if instead of taking the boundary conditions which give me the TN theory, if I choose boundary conditions that are sort of wild boundary
that's not going
conditions.
to be conformal. Yeah.
Oh, so you cannot gauge. So is there any? So okay. So
you can gauge. You can certainly gauge, but it's not manifestly conformal. It could be. It could flow still. It could flow to a conformal theory in IR, but that's something that you have to check.
I see.
And when you glue them, you integrate over the different boundary conditions, so they're not fixed anymore. They're fluctuating.
But if you fix the, I think Ali had in mind. For example, if you have a non-maximal puncture.
Yeah. Mm-hmm.
Then. Yeah.
Right.
Other questions or comments? Okay, if not, let's thank Yifan again, and we'll take a short break.
Okay. Thank you.